Hi, my name is Ravi Mangal and I'll be presenting our paper titled Probabilistic Lipschitz Analysis of Neural Networks. This is work that I've done with Kartik Sarangmath, who's an undergraduate at Georgia Tech, Aditya Nori at Microsoft Research, and my PhD advisor Alex Orso, also at Georgia Tech. First question that one may ask is, what are even neural networks? The perspective that we take in this work is to think of them as programs in a simple imperative language referred to as the cat language. This language was first presented by Tim Mangal and collaborators in 2018, and the language allows skip statements, assignment statements, sequencing of statements, and if-then-else constructs. Notice that the language has no looping constructs, but we can still express popular neural network architectures like convolutional neural nets and fully connected neural nets in this language. The assignment statement expects a linear expression on the right-hand side, where W is some constant matrix of real numbers and beta is some constant vector of real numbers. Moreover, the programs in this language produce values that are also vectors of real numbers. The Boolean expressions use a projection operation pi, where given some vector x and an index m, pi xm produces the value at the mth index of x. So all of this is fairly standard stuff, but what separates neural networks from traditional programs is that they are learned from data. This learning process is usually formalized as follows. We imagine that we are given pairs of input-output examples, and here we are using x's to refer to the inputs and y's to refer to the outputs. We are also given a search space f theta of functions or neural networks, and the goal is to find a neural network that best agrees with the data. And this goal is usually formalized as an optimization problem. Here we show one example of such an optimization problem. We say that we want to find a parameter theta such that for every xy pair, f theta of x is as close as possible to y. This optimization objective is referred to as the loss function in the machine learning literature. And as long as the loss function is differentiable and smooth, we can use geometric algorithms like stochastic gradient descent or its variants to effectively and efficiently solve the optimization problem. However, if you want to impose some additional structural or logical constraints on the optimization problem, then even the best known algorithms are computationally expensive. What this means is, if we want our neural networks to satisfy some correctness specification beyond agreement with the data, our current algorithms are too inefficient. And so the approach usually adopted in this case is to first learn a neural network that agrees with the data, and then to verify that this neural network meets some correctness spec. And that's the approach that we also take in our work. So what are these notions of correctness for neural networks beyond agreement with the data? One popular notion is that of safety, which states that bad program states can never be reached, where we define bad in some logical way. And this notion of correctness is commonly required for neural networks that are used as controllers in hybrid systems like self-driving cars or air traffic control systems. Another common notion of correctness is that of robustness, which states that small changes in the input should only lead to small changes in the output. And this notion of correctness is commonly required for neural networks employed for perception tasks like image recognition or speech recognition. Another notion of correctness that is increasingly important is that of fairness, which states that different population groups should be treated fairly for a variety of definitions of fairness. And this is becoming more and more important as we start using neural networks in decision-making algorithms. And there are a number of other notions of correctness, but in this talk, we'll focus on the notion of robustness. Why should we care about the robustness of neural networks? Well, a few years back, multiple researchers observed a very curious phenomenon. They noticed that a neural network that was trained to be an image classifier and that performed very well on test data could be easily fooled to mislabel images. So for instance, given an image of a panda that was correctly labeled by the neural network, these researchers could add some noise to the image such that the new image is visually the same as far as humans are concerned, but the neural network labels it incorrectly and does so with high confidence. And this phenomenon has been observed repeatedly for a number of different data sets for a variety of different perception tasks. And clearly this is undesirable behavior. Now, there are many ways of formalizing this notion of robustness. One very popular formalization of robustness, referred to as local robustness, says that given some input x0, for all inputs x that are less than or equal to delta distant from x0, the output of the neural network should be the same as the output at x0. This property has been heavily investigated, and there are a number of verification algorithms in the literature for checking this property. However, we are interested in a more global notion of robustness, and one way of formalizing such a global notion is to say that for every pair of inputs x prime that are less than or equal to delta apart from each other, the output of the neural network is the same or similar. This is a fairly strong property, and as we've already seen, requiring learning algorithms to produce neural networks that meet logical constraints can be very computationally expensive. In fact, we don't expect most neural networks learned using vanilla SGD to satisfy this specification. So in this work, we present a relaxed notion of global robustness that we refer to as probabilistic robustness or probabilistic Lipschitzness. We imagine that there is some distribution D from which the inputs to the neural network are drawn. And then our property states that for a pair of inputs x prime randomly sampled from D, if x and x prime are close to each other, then it should be the case that with a high probability, the distance between the outputs of the neural network for this pair of inputs should be bounded by the distance between the pair of inputs. And this notion of bounding the distance between the outputs by the distance between the inputs is referred to as Lipschitzness, and that's the motivation for naming the property probabilistic Lipschitzness. All right, before describing how to verify that a neural network is probabilistically Lipschitz, we need to describe how we represent the input distribution D. So in this work, we represent D as a probabilistic program such that this program first draws a sample from a standard Gaussian distribution and then propagates the sample through a neural network. So this combination of a random draw from a standard distribution followed by a neural network can be used to represent very complicated distributions. And in fact, this style of representing distributions has been referred to as generative modeling in the deep learning community. And they have proposed a number of approaches like generative adversarial networks, variation autoencoders, flow models for learning and describing such generative models. So in this work, we piggyback on some of these advances from the deep learning community for representing distributions. In fact, we extend the cat language to the probabilistic cat language or the pcat language, which allows us to express probabilistic programs. Syntactically, the only extension to the cat language is addition of the statement form allowing us to sample from a normal distribution. Semantically, however, the language changes quite a bit. But with this definition of the pcat language, the statistical input model or the input distribution is now simply a pcat program where we first sample from the normal distribution and append that with the program G, which represents a neural network with no source of randomness. And then assuming that the neural network that we want to prove robust is F, the pcat program under analysis is the input model or the input distribution appended with F, again assuming that F has no source of randomness. We are finally ready to describe our algorithm for verifying that a neural network is probabilistically Lipschitz. So recall that we are interested in verifying pcat programs of the form shown here. Given a pcat program in this form, a high-level sketch of the algorithm is as follows. We first pick a box-shaped input region S. We then compute S prime, which is the image of S under G. Next, we try to prove that F is K Lipschitz in the region S prime. Next, we compute the probabilistic mass of S, and then we repeat this process until necessary. So all of these steps need further elaboration, but in this talk we'll only talk about two of these steps, namely how do we prove that f is k Lipschitz in a specific region, and how do we compute the probabilistic mass of a region. I invite you to look at the paper for further details about each of these steps. In order to check if a function is k Lipschitz in a specific input region, we rely on a result from a paper by Wang et al. That appeared in ICLR 2018. So this result says that given some input region S and given some function f from Rn to Rn, where f can be represented by a cat program, the Lipschitz constant k of f in the region S is given by the maximum of the operator norm values for the Jacobians of f in S, where the Jacobian is the counterpart of the gradient for vector valued functions. So in other words, the Jacobian of f at x is a matrix where each element of the matrix is a partial derivative of f at x. So using this result, if we can compute the max of these operator norm values, we can also compute the Lipschitz constant k of f in a specific region. So we design an analysis that we refer to as the Jacobian analysis that helps us over approximate this max operator norm value. Essentially, this Jacobian analysis computes lower and upper bounds for each element of the Jacobian matrices of f in S. In other words, the analysis computes an interval for each element of the Jacobian matrix, and all the corresponding partial derivatives of f in S are guaranteed to lie in this interval. And we can then use this interval or this abstract Jacobian matrix of intervals to compute an over approximation of the maximum operator norm value. And this analysis is a flow sensitive, path insensitive analysis. And the design of this analysis is heavily inspired by the fast lip algorithm from a different set of authors that appeared in an ICML 2018 paper. The next thing to look at is how do we compute the probabilistic mass of input regions as a step in our verification algorithm. So it's been long known that computing the volume of convex bodies even in standard Euclidean spaces is hard, meaning the time complexity is beyond polynomial. Also, the best known algorithm for approximately computing the Gaussian volume of convex bodies has time complexity O to the n cube, where n is the number of dimensions, and in standard deep learning settings, the number of dimensions can be on the order of thousands or even millions. Note that by Gaussian volume here, we mean the probabilistic mass of a convex body with respect to a Gaussian distribution. So the design of our algorithm, we have been very conscientious about avoiding complex volume computations. And we do this by only ever requiring the computation of Gaussian volume of box-shaped convex bodies. And this computation can be performed in linear time via a simple lookup in the standard normal table, or what is also referred to as a Z table. We performed a small empirical evaluation to evaluate the running time of our algorithm. And we asked two research questions. So our first research question was to ask, given a specific pcat program, is the running time of each iteration of our algorithm affected by the size and the location of the box-shaped region that is picked as the input region to explore. Our second research question was to ask, what is the running time of each iteration of our algorithm on some popular generative models and neural networks, meaning on some popular pcat programs. Okay, so here are our empirical results. We consider three different pcat programs. Our first pcat program is a classifier of digits from the MNEST dataset. Our second pcat program is a classifier of images from the CFAR10 dataset. And our third pcat program is also a classifier of images from the CFAR10 dataset, but this classifier is much larger and more accurate than the second program. For each of these pcat programs, the generative model that we use is some publicly available model for the corresponding data set. Moreover, for each pcat program, we consider 5 different locations for the input boxes, and these 5 locations are randomly picked. For each location, we consider 3 different box sizes indicated by the 3 different colors. So each bar basically corresponds to the running time of the algorithm when we consider a specific box of a specific size for a specific program. The running time is indicated on the y-axis. So with respect to our first research question, which asks about the effect of the box location and the box size on the running time, we see that the location does not really affect the running time, and this trend persists for all 3 programs. But the size of the box does affect the running time, and this is because our algorithm actually performs some pruning of the neural network, which depends on the input region considered. So if we have a larger box that we consider, we are able to prune a smaller fragment of the neural network, which means that the algorithm has to analyze a larger fragment of the program. And this is reflected in the fact that larger box sizes lead to an increase in the running time. With respect to our second research question, which asks about the effect of the program or the program size on the running time, we again clearly see that larger programs require longer running times. And this trend exists for all the 3 programs, and we expect it to continue for even larger programs. Alright, that is all I have to say about our verification algorithm, and I would like to briefly highlight some open questions that we think are particularly relevant to the work presented here. The first open question that we would like to address is how should our verification algorithm pick the input regions? And we expect that the strategy for picking these input regions would play a key role in the scalability of the algorithm. Another question that we would like to address is how should we deal with a situation where the input distribution changes at runtime? So our algorithm assumes that the input distribution stays fixed. To address this, we would need to design an algorithm that can prove a neural network to be probabilistically Lipschitz with respect to a family of distributions as opposed to just a single distribution. We would also like to extend our algorithm to handle the verification of neural networks with loops. And this would allow us to verify neural network architectures like recurrent neural networks or LSTMs. Our paper has many more details. We describe the denotational semantics of the pcat language. We give details of the Jacobian analysis using the abstract interpretation framework. We provide a proof of correctness of our verification algorithm. There's a detailed discussion about probabilistic robustness and algorithmic trade-offs in verifying different notions of robustness. There are also some empirical results about the running time of our algorithm. So I invite you to look at the paper and contact me or any of the other authors in case you have any feedback or comments. To conclude, we present probabilistic robustness as a possible specification for correctness of neural networks. In particular, we think of probabilistic robustness as a practical way of capturing a global notion of robustness of neural networks. We formalize our problem in a language theoretic framework, and we design our analysis using the abstract interpretation framework. We present an algorithm for verifying this probabilistic notion of robustness, and we also present a Jacobian analysis that can compute an upper bound on the Lipschitz constant of a neural network in a specific region. And our code is available at this link. With that, I conclude, and thank you for your attention.